Imagine you could send a message faster than light. Sounds incredible, right? Like the ultimate communication breakthrough. But here is the problem. If you could do that, you could send a message into your own past. You could receive an answer before you even asked the question. Cause and effect would shatter. Reality itself would collapse into paradox. This is not science fiction. This is the foundation of modern physics. And it all started with one man's revolutionary insight about the universe. Albert Einstein believed the cosmos operates under an absolute rule. Nothing, absolutely nothing, can travel faster than light. Not matter, not energy, not information, not even gravity itself. 300,000 kilometers per second. That is the ultimate speed limit of reality. Break it, and you break the universe. But why? What makes this speed so special? Why does nature enforce such a strict boundary? The answer lies in something far stranger than you might expect. It is not just about speed. It is about the very fabric of cause and effect, about whether reality makes sense at all. And as we will discover, quantum mechanics threatens to tear this fabric apart. Let us go back to the beginning. Before Einstein, Isaac Newton ruled physics. Newton gave us gravity, the force that keeps planets in orbit and holds galaxies together. But Newton's gravity had a deeply troubling feature. It acted instantly across any distance. Earth orbits the Sun because the Sun pulls on Earth. But according to Newton, if the Sun suddenly vanished, Earth would instantly feel the loss. No delay, no waiting. Just immediate action across 150 million kilometers of empty space. Newton himself found this idea disturbing. He called it action at a distance and admitted he could not explain how it worked. In a letter to a colleague, Newton confessed that the idea of one body acting upon another through empty space, with no mediating substance, seemed absurd, yet his equations worked perfectly. They predicted planetary motions with stunning accuracy. So physicists accepted instant gravity, even though it felt deeply wrong. For 2 centuries, nobody seriously challenged this assumption. Instant action at a distance became scientific common sense. Then Einstein arrived. Einstein showed that instant gravity creates impossible paradoxes. Here is why. According to relativity, observers moving at different speeds experience time differently. They disagree on whether 2 distant events happen simultaneously. Imagine 2 explosions happening light years apart. One observer, standing still, sees them occur at the same moment. Another observer, flying past at high speed, sees one explosion happen before the other. A third observer, flying in the opposite direction, sees them in reverse order. This is not illusion. This is reality. Time is relative. Simultaneity is relative. There is no universal now that everyone agrees on. Now, add instant gravity to this picture. Suppose the Sun tugs on Earth instantly. For some observers, that tug arrives before it even leaves. Effect precedes cause. The universe becomes self-contradicting. Events trigger themselves. Logic fails. Einstein realized something profound. If you allow faster-than-light effects, some observers will see events in reverse order. A message sent faster than light becomes, for certain observers, a message traveling backward in time. You could theoretically reply to yourself before sending the original message. You could create causal loops, grandfather paradoxes, time travel nightmares. The only way to prevent this logical catastrophe is to enforce a cosmic speed limit. Nothing can exceed light speed. Not because light is special, but because causality is sacred. Cause must precede effect, always. For every observer, without exception. This forced Einstein to completely reimagine gravity. If gravity cannot act instantly, what is it really? How does Earth know the Sun is there? How does gravitational influence propagate through space? Einstein's answer was revolutionary. Gravity is not a force pulling through empty space. Gravity is space-time itself, curved and warped by the presence of mass. The Sun does not pull on Earth. The Sun bends the fabric of space-time, and Earth follows the curved path through that bent geometry, like a marble rolling along a curved rubber sheet. When something massive moves, it creates ripples in space-time. These ripples spread outward at exactly the speed of light. Gravitational changes propagate like waves across the cosmos. If the sun vanished, Earth would continue orbiting for 8 minutes and 20 seconds. The time light takes to travel from sun to Earth. Only then would Earth feel the change and drift away into darkness. This discovery reshaped physics completely. The universe enforces a speed limit not out of arbitrary rules, but because reality itself depends on it. Relativity demands this limit to remain logically consistent. The cosmic speed limit protects causality. It preserves the logical structure of reality. For decades, physicists celebrated this achievement. Einstein had solved the mystery of gravity and secured the foundations of cause and effect. The universe made sense again. Instant influences were banned. Locality reigned supreme. Every effect had a local cause, propagating no faster than light. Then quantum mechanics arrived, and everything fell apart. Because quantum theory predicts something impossible, something that should not exist, something that threatens everything Einstein built. Quantum mechanics allows instantaneous effects across vast distances. It permits correlations that appear faster than light. It seems to violate locality itself. And the most disturbing part, every experiment confirms quantum mechanics is right. So now we face an impossible choice. Either relativity is incomplete or quantum mechanics is wrong, or reality is far stranger than either theory suggests. One of the deepest mysteries in physics emerges from this conflict. How can both theories be correct? How can nature enforce a cosmic speed limit while simultaneously violating it? The answer will take us through entangled particles, philosophical battles, experimental revelations, and finally to interpretation so radical it suggests infinite parallel universes. But it all begins here with Einstein's simple but profound insight. The universe has a speed limit, and breaking it would break reality itself. We left off with a troubling question. Einstein had just established the cosmic speed limit, protecting causality and making the universe logically consistent. Nothing could travel faster than light. Nothing could act instantaneously across distance. Reality made sense. Then quantum mechanics shattered everything. The quantum revolution began innocently enough. Physicists were studying atoms, light, and the behavior of particles at the smallest scales. What they discovered defied all intuition. The microscopic world operated by rules completely alien to everyday experience. At the heart of quantum mechanics lies something called the wave function. Think of it as a mathematical description of a particle's state. But here is where things get strange. The wave function does not tell you where a particle is. It tells you where it might be. It describes possibilities, not certainties, probabilities, not facts. Before you measure a particle, it exists in multiple states simultaneously. An electron does not have a definite position. It has a cloud of possible positions. A photon does not have a definite polarization. It exists in a superposition of all polarizations at once. The particle is literally in multiple states, occupying many configurations simultaneously, spread across space like a ghost. This is not ignorance. This is not about what we know. This is about what exists. According to quantum mechanics, particles genuinely inhabit multiple realities at once until something forces them to choose. That something is measurement. When you measure a quantum particle, something dramatic happens. The wave function collapses. All those possibilities vanish instantly. The particle suddenly acquires a definite state. The electron appears at one specific location. The photon adopts one specific polarization. Reality crystallizes from a haze of possibilities into a single concrete outcome. And here is the deeply disturbing part. This collapse happens instantly. Not almost instantly, not very quickly, instantly, everywhere at once across any distance, without delay. Imagine an electron whose wave function is spread across an entire laboratory. You measure it on the left side of the room and find it there. At that exact instant, the wave function on the right side of the room vanishes. Gone, immediately. The probability of finding the electron there drops to zero faster than light could travel across the room. Distance does not matter. Whether the wave function extends across a room, across a continent, or across the galaxy, collapse occurs everywhere simultaneously. The entire wave function, no matter how vast, responds instantly to a measurement performed at one location. This violates locality. Locality is the principle that says objects are only influenced by their immediate surroundings. What happens here cannot instantly affect what happens there. Information and influence must propagate through space, taking time to travel from place to place. Locality is the foundation of relativity. It protects causality. But wave function collapse ignores locality completely. Einstein saw this problem immediately. In 1935, he exposed this contradiction publicly, challenging the physics community to confront what quantum mechanics was really claiming. According to the theory, measurement here determines reality there, instantly, regardless of distance. The act of observing a particle in one location forces a corresponding change everywhere the particle's wave function extends. This seems to contradict everything relativity teaches. How can a measurement here affect reality over there faster than light can travel between them? How can information leap across space without crossing the space in between? How can the universe maintain Einstein's cosmic speed limit while permitting instantaneous effects? The paradox gets worse. Quantum mechanics does not just allow this strange behavior, it requires it. The theory's predictions depend on instantaneous collapse. Without it, quantum mechanics fails to match experimental results. And those results are spectacularly accurate. Quantum theory is the most precisely tested scientific theory in history. Its predictions match reality to more than 10 decimal places. It has never been wrong. Not once. So we face an impossible situation. Quantum mechanics predicts reality perfectly. Its mathematical framework produces correct answers for every experiment ever performed. Yet its physical interpretation creates deep paradoxes. It demands instantaneous effects that should not exist. It requires non-local influences that violate the cosmic speed limit. How can both be true? How can quantum mechanics be perfectly accurate while simultaneously contradicting relativity? Some physicists tried to dismiss the problem. They claimed wave function collapse was just mathematics, not physical reality. They said quantum mechanics only predicts measurement outcomes and we should not ask what happens between measurements. They insisted the paradox was philosophical, not scientific. But Einstein refused to accept this evasion. He believed physics should describe reality, not just predict experimental results. If quantum mechanics forces us to accept instantaneous collapse, we need to understand what that means physically. We cannot simply ignore the contradiction and pretend it does not exist. The debate divided physics into two camps. On one side stood those who accepted quantum mechanics as complete, who believed the wave function contains all possible knowledge about a system, who thought asking about reality between measurements was meaningless. On the other side stood Einstein and those who insisted reality must exist independently of observation, who believed quantum mechanics was incomplete, who thought deeper explanations must exist beneath the probabilistic surface. This was not merely academic argument. This was a battle over the nature of reality itself. Does the universe exist when nobody is looking? Do particles have definite properties before measurement? Is reality fundamentally random, or does determinism hide beneath quantum uncertainty? And most crucially for our story, does nature truly permit faster than light influence? Does quantum mechanics really violate locality? Or is there something we have misunderstood, something that reconciles quantum mechanics with relativity without destroying either theory? The answer would not come from philosophical debate. It would come from one of the most profound thought experiments in physics history, an experiment so clever it would eventually force nature itself to answer these questions. An experiment involving two particles separated by vast distances, yet mysteriously connected in ways that seem to violate everything Einstein held sacred. That experiment begins with entanglement, and entanglement is where quantum mechanics becomes truly spooky, because entangled particles do not just seem to communicate faster than light. They appear to share a single identity across space, to remain mysteriously coordinated no matter how far apart they travel. They behave as if distance has no meaning, as if they are somehow still one object despite being separated by meters, kilometers, or light years. Einstein called this spooky action at a distance and used it to argue quantum mechanics must be incomplete. But he could not have imagined where this argument would lead. He could not have predicted that decades later, scientists would perform actual experiments with entangled particles, and he certainly could not have anticipated what those experiments would reveal about the nature of reality itself. We have reached the moment where physics split into two worlds. On one side stood Albert Einstein, defender of reality and locality. On the other stood Niels Bohr, champion of a radical new interpretation that would reshape how we think about existence itself. This was not a polite academic disagreement. This was a fundamental clash over what science should even try to accomplish. And the outcome of this battle would determine how physicists understood quantum mechanics for nearly a century. Niels Bohr was a Danish physicist working in Copenhagen. In the 1920s, he and his colleagues developed what became known as the Copenhagen interpretation of quantum mechanics. This interpretation did not merely explain the mathematics, it made bold philosophical claims about the nature of reality. According to Bohr, physics should only predict measurements. That is all. The job of quantum mechanics is to tell us what we will observe when we perform experiments. Nothing more. The wave function is simply a tool for calculating probabilities of measurement outcomes. It does not describe an independent reality existing out there in the world. But Bohr went further, much further. He claimed that asking about reality between measurements is meaningless, not difficult, not unknown, meaningless. When you are not measuring an electron, the question "where is the electron?" has no answer because the electron does not have a location. Properties only exist at the moment of measurement. The rest of the time there is only the wave function, a mathematical abstraction encoding possibilities. This sounds insane. It feels like denying that the moon exists when nobody looks at it. But Bohr argued this was precisely the lesson quantum mechanics teaches. Reality is not independent of observation. Measurement does not reveal pre-existing properties. Measurement creates properties. The act of observation brings reality into being. For Bohr and the Copenhagen interpretation, the wave function contains all possible knowledge about a quantum system. There is nothing deeper, nothing hidden, nothing beyond what the mathematics describes. Quantum mechanics is complete. The probabilistic nature is fundamental. The universe is genuinely random at its core. Einstein hated this interpretation with a passion that consumed him for the rest of his life. He called the Copenhagen interpretation a tranquilizing philosophy, designed to make physicists stop asking difficult questions. He believed it was intellectual surrender disguised as profound wisdom. To Einstein, Copenhagen was not solving the measurement problem. It was declaring the problem meaningless and walking away. Einstein's objections ran deep. He believed reality exists independently of observation. The universe does not need us to look at it to be real. Particles have definite properties whether we measure them or not. Physics should describe this independent reality, not just predict measurement outcomes. More importantly for our story, Einstein was profoundly disturbed by non-local collapse. The instantaneous wave function collapse that quantum mechanics required seemed to violate everything relativity taught about locality and the cosmic speed limit. If measurement here instantly affects reality there, how can we maintain that nothing travels faster than light? Einstein saw two possibilities. Either quantum mechanics was incomplete, hiding deeper variables that would restore locality and determinism, or quantum mechanics was simply wrong. But he could not accept that nature truly permitted faster than light influence while simultaneously forbidding faster than light travel. The contradiction seemed too blatant, too fundamental to ignore. Bohr disagreed completely. He argued that quantum mechanics was fully consistent with relativity because wave function collapse does not transmit usable information. You cannot control what outcome you get when you measure a particle. The results are random, so even though collapse happens instantaneously, you cannot exploit it to send messages faster than light. Therefore, no paradox exists. But Einstein was not satisfied. His objection went deeper than communication. He believed that any influence, even random influence, traveling faster than light, violated the spirit of relativity. The cosmic speed limit was not just about sending messages. It was about maintaining causality and locality as fundamental principles of nature. The debates between Einstein and Bohr lasted for decades. They met at conferences, exchanged letters, published papers challenging each other's views. Einstein would devise clever thought experiments showing apparent contradictions in quantum mechanics. Bohr would analyze them carefully and explain why quantum mechanics remained consistent. Here is the tragic part. Bohr often misunderstood Einstein's actual arguments. Historical analysis of their debates reveals that Bohr frequently responded to positions Einstein never held. Einstein was not questioning whether quantum mechanics made correct predictions. He was questioning whether the Copenhagen interpretation was the only way to understand those predictions. He was asking if deeper explanations might exist beneath the quantum surface. But Bohr's authority was immense. He was charismatic, persuasive, and surrounded by brilliant students who spread the Copenhagen interpretation throughout the physics world. Einstein, meanwhile, worked increasingly alone, pursuing ideas that mainstream physics considered misguided or obsolete. History favored Bohr. The Copenhagen interpretation became the standard way to teach quantum mechanics. Textbooks presented it as settled truth. Physicists learned to shut up and calculate to use the mathematics without worrying about philosophical foundations. Questions about the nature of reality, about what exists between measurements, about whether particles have definite properties, all these questions were dismissed as unscientific or meaningless. For decades, studying the foundations of quantum mechanics was considered a waste of time. Young physicists were discouraged from asking such questions. The field stagnated philosophically, even as it achieved spectacular technological successes. We learned to build quantum devices, to exploit quantum effects, to make incredibly precise predictions. But we stopped asking what it all meant. Einstein never stopped asking. Even late in life, when most physicists dismissed his concerns, he continued arguing that quantum mechanics must be incomplete. He believed that beneath the probabilistic wave function, reality was deterministic and local. Hidden variables must exist that determine outcomes while preserving Einstein's cosmic speed limit. But Einstein lacked proof. He could point to philosophical problems and logical tensions, but he could not demonstrate that quantum mechanics was actually wrong or incomplete. He could not propose an alternative theory that made different, testable predictions. Without experimental evidence, the debate remained philosophical, and philosophical debates do not change physics, only experiments do. What Einstein needed was a way to transform his philosophical objections into testable predictions. He needed an experiment that could distinguish between quantum mechanics and local realism. He needed nature itself to choose between his worldview and Bohr's. In 1935, Einstein finally found that experiment. Together with two younger colleagues, Boris Podolsky and Nathan Rosen, Einstein published a paper that would become legendary. A paper describing a phenomenon so strange, so counterintuitive, that Einstein believed it proved quantum mechanics must be incomplete. That phenomenon was entanglement, and the thought experiment they described would eventually lead to real experiments that forced nature to reveal which interpretation was correct. Experiments that would shock the physics community. Experiments that would prove nature really does violate locality, that faster-than-light influence genuinely exists, that Einstein's worldview could not survive. But those experiments were still decades away. First, we need to understand exactly what entanglement is, why it troubled Einstein so deeply, and how it seemed to permit instantaneous communication across arbitrary distances. We need to understand the EPR paradox. In 1935, Einstein, Podolsky, and Rosen published a paper with a deceptively simple title: Can quantum mechanical description of physical reality be considered complete? This paper, now known simply as EPR, introduced the world to quantum entanglement and created a paradox so profound it would haunt physics for generations. The EPR paper was Einstein's most sophisticated attack on quantum mechanics. It was not a philosophical rant or a vague complaint. It was a precise logical argument demonstrating that quantum mechanics, as interpreted by Bohr, led to an impossible choice. Either the theory was incomplete or nature permitted instantaneous influence across arbitrary distances. Einstein believed he had finally cornered quantum mechanics into admitting its flaws. He was wrong, but the way he was wrong turned out to be far stranger than anyone imagined. Let me explain what entanglement actually is, because it is the key to everything that follows. Imagine creating two particles from a single quantum event. Perhaps a photon splits into two photons, or a particle decays into two particles. These particles fly apart in opposite directions. They separate by meters, then kilometers, then light years. But quantum mechanics says something bizarre about them. They are not two independent particles. They are one quantum system described by a single shared wave function. It was an elegant solution. It preserved everything Einstein valued: realism, locality, determinism, causality. It explained the perfect correlations without invoking spooky action at a distance. It suggested quantum mechanics was just an approximation, a statistical theory that worked well but missed the underlying deterministic reality. Bohr responded to the EPR paper, but his response was convoluted and unsatisfying. He argued that the particles could not be considered as having independent reality once they became entangled. Measurement on one particle was not revealing a pre-existing property, but creating a property that the entire entangled system must respect. The EPR paradox, in Bohr's view, simply demonstrated the limitations of classical thinking when applied to quantum systems. But Bohr could not prove Einstein wrong. Einstein could not prove quantum mechanics incomplete. The debate reached a stalemate. Both interpretations seemed to fit the experimental facts. Both could explain the perfect correlations between entangled particles. The question seemed destined to remain forever philosophical, beyond the reach of experimental testing. For 30 years, that is exactly what happened. Physicists largely ignored the EPR paper. They treated entanglement as a curious theoretical feature with no practical importance. They continued using quantum mechanics successfully while avoiding deep questions about its interpretation. The foundations of quantum theory remained frozen in the disagreement between Einstein and Bohr. Then, in 1964, everything changed. A physicist named John Bell working at CERN decided to take Einstein's hidden variable proposal seriously. Bell asked a simple question: if hidden variables exist, what exactly would they predict? Could we design an experiment to test whether nature uses hidden variables or genuine quantum entanglement? Bell discovered something astonishing. He proved that hidden variables and quantum mechanics make different predictions. Not for all experiments, but for carefully designed ones measuring entangled particles along different angles. He derived mathematical inequalities that any local hidden variable theory must satisfy, and he showed that quantum mechanics violates these inequalities. Nature would have to choose, either local hidden variables or quantum mechanics. Both could not be right. By the end of the EPR story, it looked as if the argument between Einstein and Bohr might never be settled. Both sides had powerful reasoning. Both sides could claim to respect the known experiments. And for decades, most physicists simply moved on, using quantum mechanics as a tool, without worrying too much about what it meant. Then John Bell appeared, and quietly changed everything. Bell was not a celebrity physicist. He was working at CERN, known mainly as a thoughtful theorist, who took foundational questions seriously at a time when most people did not. Where others saw philosophy, Bell saw an opportunity for a precise calculation. He wondered, very simply, what would actually happen if Einstein's idea of local hidden variables were true. Remember what Einstein hoped for. He wanted a theory where entangled particles carried hidden instructions from the start. No spooky action at a distance, no faster-than-light influence. Just particles behaving according to pre-existing properties, with correlations explained by common causes in their shared past. That picture feels safe, almost comforting. Bell asked a sharp question: if particles really carry such hidden information, and if no influence can travel faster than light, are there any limits on how often their measurement results can disagree or agree when we test them in different ways? In other words, can we turn locality and hidden variables into a numerical prediction that can be compared with quantum mechanics? He found that we can. Bell derived what are now called Bell inequalities. They are strict mathematical constraints that any local hidden variable theory must obey. They do not depend on the details of the hidden variables. They only rely on two core assumptions that Einstein strongly believed in. First, locality. Nothing done to one particle can instantly affect the other if they are far apart. Second, realism. Measurement results reflect properties that existed before and independent of the act of measurement. From these assumptions, Bell showed that if you perform clever experiments on entangled pairs, the statistics of the outcomes must obey specific limits. In particular, if you and a partner choose different orientations for your spin measuring devices, there is a minimum level of disagreement that any local hidden variable theory must produce. Here is where it becomes striking. Quantum mechanics predicts a different pattern. According to quantum theory, if you choose measurement directions with certain relative angles, the probability that the outcomes disagree is about 25%. A local hidden variable theory, obeying Bell's assumptions, predicts at least 33% disagreement for the same settings. That difference is huge. It is not a tiny effect hidden in experimental noise. It is a clear, testable prediction. If nature gives 25%, quantum mechanics wins and local hidden variables die. If nature gives 33% or more, Einstein's dream survives and the Copenhagen view is incomplete. For the first time, the conflict between Einstein and Bohr was no longer philosophical. It became experimental. Nature could be asked directly. But there was a practical problem. When Bell published his result in 1964, the technology to perform such delicate experiments with entangled particles barely existed. The idea was ahead of its time. For almost 2 decades, Bell's theorem remained a brilliant, little-known insight. A few people understood its importance, but the wider community did not yet feel the impact. That changed in the 1980s, thanks to a French physicist named Alain Aspect. Aspect and his team developed experimental techniques to produce pairs of entangled photons and send them to far-separated detectors. They could choose different measurement settings for the polarization of each photon and record how often the results matched or differed. Aspect performed a series of Bell tests. They were carefully designed to close as many loopholes as possible. The detectors were placed far enough apart so that any signal traveling at or below the speed of light could not coordinate the choices of measurement settings in time. The setup was built precisely to test Bell's inequalities under conditions where locality should hold if nature were local. The results were astonishing. The data matched the predictions of quantum mechanics almost perfectly. The rate of disagreement in the outcomes was around 25%, just as quantum theory expected. The Bell inequalities, which any local hidden variable theory must satisfy, were violated. Local hidden variables failed. Nature does not behave like Einstein hoped. The correlations between entangled particles are stronger than any local hidden instruction set can explain. No theory that keeps both locality and realism in the way Einstein imagined can reproduce the observed statistics. The conclusion is inescapable. Nature violates locality. There are correlations between distant events that cannot be explained by any influence traveling at or below the speed of light from one to the other. In this precise, technical sense, faster than light influence exists, and yet a second remarkable fact emerges. Even though these influences seem to exceed the speed of light, they cannot be used to send messages faster than light. You cannot control the outcomes of quantum measurements. Each individual result is random. When you and a distant partner measure entangled particles, you each see a string of random outcomes. Only when you later compare your results do you discover the amazing correlations. This is the subtlety that protects causality. Quantum mechanics allows non-local correlations but blocks controlled faster-than-light communication. You cannot use entanglement to send a signal into your own past. You cannot build a time travel device from Bell violations. Randomness acts like a cosmic censor, allowing nature to violate locality while preventing paradoxes. So where does this leave Einstein's cosmic speed limit? On one level, it survives. No object, no signal, no usable information can travel faster than light. Relativity remains correct in its domain. On another level, the universe is more deeply non-local than Einstein ever allowed himself to believe. There is structure in reality that does not respect the separation of space in the classical way. Bell's theorem ended the old debate. It forced physicists to accept that any complete description of quantum phenomena must be non-local in some sense. We can no longer cling to the idea that all influences propagate within light speed limits through ordinary space. Something more subtle and more puzzling is at work, but Bell did not tell us what that something is. He only told us that local hidden variables are impossible. He shut one door and left us in a room full of new, unsettling possibilities. If nature is non-local, what kind of picture of reality can we build that respects both quantum mechanics and relativity? How do we talk about a world where entanglement is real, Bell violations are real, and yet no signal outruns light? One answer, perhaps the most radical and influential, is the many worlds interpretation. It removes wave function collapse entirely, keeps the quantum wave function as the only reality, and claims that every possible outcome of every quantum measurement actually happens, each in its own branching universe. In that picture, entanglement does not require faster-than-light influence at all. It becomes a local process in a much larger, stranger structure. If that sounds extreme, it is. But it may be the only way to save Einstein's deepest intuition while still accepting Bell's experimental verdict. To see how that works, we must step into a universe that is constantly splitting, a reality where every quantum event creates new branches of existence, a world where nothing ever truly collapses, and where Einstein's dream of locality might survive in a form he never imagined. We have arrived at the strangest conclusion of our journey. Bell's experiments proved that nature violates locality. Faster-than-light influence exists. Einstein's dream of a purely local universe seemed dead. The cosmic speed limit that protected causality appeared fundamentally incompatible with quantum mechanics. But what if there is another way? What if we have been thinking about quantum mechanics incorrectly from the very beginning? What if the problem is not with locality, but with our assumption that wave functions collapse? This is where the many worlds interpretation enters, and it changes everything. The many worlds interpretation was proposed by Hugh Everett in 1957, while he was still a graduate student. At the time, almost nobody took it seriously. It seemed too radical, too extravagant, too philosophically unsettling. But over the decades, it has gained support among physicists who take the mathematics of quantum mechanics at face value. Here is the core idea. There is no wave function collapse. None. Ever. In the standard Copenhagen interpretation, measurement causes the wave function to suddenly jump from describing multiple possibilities to describing a single outcome. This collapse is what creates the faster-than-light influence that troubled Einstein. When you measure an entangled particle here, the wave function over there instantly changes. Many worlds says this never happens. The wave function always evolves smoothly according to the Schrödinger equation, the fundamental equation of quantum mechanics. No jumps, no discontinuities. No magical moment where possibilities become actualities. The wave function of the universe continuously branches into parallel versions, and all outcomes occur in different branches. Let me explain what this means for measurement. When you observe a quantum particle in superposition, you do not force it to choose one state. Instead, you become entangled with it. The universe splits. In one branch, you observe outcome A, and the particle has state A. In another branch, you observe outcome B, and the particle has state B. Both versions of you exist, in different branches of reality, each convinced they saw a definite result. There is no collapse because nothing disappears. All possibilities remain real. They just exist in different, non-interacting branches of the universal wave function. What we call measurement is simply branching. What we call randomness is simply our ignorance of which branch we inhabit. This sounds completely insane. It sounds like science fiction masquerading as physics. But here is the remarkable thing. Many worlds might actually solve the locality problem. Remember the EPR paradox and Bell's theorem. The issue was that measuring one entangled particle instantly determines the state of the other, even across vast distances. This seemed to require faster-than-light influence, but many worlds offers a different picture. When entangled particles separate, they carry correlated information in their shared wave function. This correlation was established when the particles were created together, locally, in the same place. No faster-than-light influence was needed to create the correlation. It emerged from a local interaction in the past. Now you measure one particle. In the many worlds picture, the universe branches. In some branches you find spin-up. In other branches you find spin-down. But here is the key. Your measurement does not instantly affect the distant particle. It affects you. You become entangled with the particle you measured. The branching happens locally, at your location. The distant particle still exists in superposition. Its wave function has not changed. No signal travelled to it. No influence reached across space faster than light. From its perspective, nothing happened yet. Only when your measurement result and the distant particle's measurement result are later compared do the correlations become apparent. And by that time, information about both measurements has propagated through ordinary space, respecting the cosmic speed limit. The correlation was always there, encoded in the entangled state from the beginning. The measurements simply reveal it branch by branch. In many worlds, Bell's assumptions no longer apply in the same way. Bell assumed that each particle has a definite measurement outcome and that locality prevents coordination between distant outcomes. But many worlds denies the first assumption. There is no single definite outcome. All outcomes occur. The apparent coordination is explained by the branching structure of reality, not by faster-than-light signals. The entanglement spreads locally through space as the particles separate. The wave function evolves according to local differential equations. Every interaction is local in space-time. The appearance of non-locality emerges only when we mistakenly assume wave function collapse creates a single outcome. This means many worlds potentially restores locality while keeping quantum mechanics intact. There is no faster-than-light influence because there is no collapse. The correlations that violate Bell inequalities are explained by the branching structure of reality, not by instantaneous communication between distant particles. Even observers become entangled with the systems they measure. You, reading this now, are entangled with countless quantum systems around you. In the many worlds picture, there are versions of you in different branches experiencing different outcomes. Each version is convinced they live in a single, definite reality, but the complete picture includes all branches simultaneously. This resolves the paradox between quantum mechanics and relativity. Relativity forbids faster-than-light signals. Many worlds has no faster-than-light signals because it has no collapse. Quantum mechanics requires perfect correlations between entangled particles. Many worlds explains these correlations through branching, not through non-local influence. Locality is preserved. The cosmic speed limit survives. Einstein's deepest intuition about the structure of space-time might be vindicated after all, just not in the way he imagined. But the price is extraordinarily high. We must accept that reality is infinitely branching. Every quantum event, every interaction, every measurement creates new parallel universes. The number of branches grows exponentially. Every possible outcome of every quantum process occurs somewhere in the vast tree of branching worlds. This is deeply unsettling. It violates every intuition we have about the uniqueness of reality. It suggests that countless versions of you exist, making different choices, experiencing different outcomes, living different lives. It makes the universe unimaginably larger and stranger than we ever conceived. Many physicists find this too extravagant to accept. They argue that postulating infinite parallel universes just to avoid wave function collapse is absurd. Others respond that we should take the mathematics of quantum mechanics seriously, and the mathematics naturally describes branching without collapse. The debate continues, but what is clear is this. If you want to preserve locality, if you want to keep Einstein's cosmic speed limit as a fundamental principle, if you want quantum mechanics and relativity to peacefully coexist, Many Worlds offers a potential path forward. It suggests that the universe is far stranger than either Einstein or Bohr imagined. Not because faster-than-light influence exists, but because reality itself is vastly more complicated than a single timeline of events. The non-locality revealed by Bell's experiments is not about signals travelling faster than light. It is about the structure of reality being fundamentally branched. Perhaps Einstein was right that locality is sacred. Perhaps faster-than-light influence really is forbidden. But preserving that principle requires accepting something even more bizarre than spooky action at a distance. It requires accepting that we live in a constantly splitting multiverse, where all possibilities are real. This is where our journey ends. We started with Einstein's cosmic speed limit, the principle that nothing can exceed light speed. We discovered that quantum mechanics seems to violate this through instantaneous wave function collapse. We watched Einstein and Bohr battle over the interpretation. We learned about entanglement and the EPR paradox. We saw Bell's theorem force nature to reveal its non-local character through experiment. And now we face a choice. Either accept that faster-than-light influence exists while somehow not allowing faster-than-light communication, or embrace many worlds, restore locality, keep Einstein's dream alive, but at the cost of accepting infinite parallel realities. Nature has spoken through experiment. How we interpret that voice remains the deepest open question in physics. Einstein's dream may survive after all, but in a form more radical and more wonderful than he ever dared to imagine.